Okay, so let me first finish the remainder of uh, the syllabus-related material, and then I will start talking about this. For example, I will start with sequence alignment method, or maybe the phylogenetic tree method that I mentioned as an example lecture. I may start talking about the neighbor joining algorithm. So let's see whether you'll or the UPGM algorithm, which is simpler, whether you'll be able to follow that problem and the solution. And then you can decide whether you want to take the course for credit or not. All right, so I'm going to share the link to the form at the end of the class again. So if you want to take the course, you may write your name, student ID, everything on that form and submit, and you will be able to uh, add the course. Again, you will have to do it manually on your own, but your student ID will be added to the criteria, so you will be able to edit during the add drops next week. All right. So we have a teaching assistant for this course, Hazal. She's basically going to grade your assignments. You may also ask questions to her, but you can also ask your questions to me directly by email or by submitting your questions on the forum on OTClass. And in terms of grading, the exams are going to basically comprise most of your total grade. 80% of your total grade will be coming from midterm and final exams, which are going to be conducted online. And you may have to have your camera on during the exam. So I will post the details about how we're going to conduct the exam when the time comes. But mostly it will be a synchronous online exam, not take-home. No, it's not going to be a take-home exam. It's going to be a synchronous online exam where you may be required to turn on your cameras. And you're going to have 4 assignments, 5% each, and probably 2 of them are going to be programming and 2 written assignments. And in terms of online material, I already went over the course website. I will be using OTClass mainly for you will be submitting your assignments on OTClass. There will be announcements there, and you will also see your grades. Your grades for the assignments and the exams are going to be posted on OTClass. And I will open up a forum for students in which you can discuss among your classmates. The news group, I will not be using it myself mainly because there will be students in our class from other departments. There may be students from the graduate programs like the Bioinformatics graduate program, the Bioinformatics master's program. This course is a must course in the graduate Bioinformatics master's program. So we will have students from there, which those students will not have a computer engineering account, so they will not be able to access CAL. That's one of the reasons I'm not going to be using CAL mainly for class-related assignments and stuff, but our computer engineering students you're welcome to conduct discussions on CAL as well. All right, so this is computer engineering on the web. So the molecular biology introduction, I'm going to go over these slides, the molecular biology introduction, the introduction to biology, and the required for targeted towards computer engineering students. I will go over them this Thursday at 12:30. So our second lecture this week is on Thursday. So I will do that on Thursday. All right. So I'm going to skip the remaining slides. So all these remaining parts, the introduction, molecular biology introduction, the introduction to different types of data, I will go over them on Thursday. Now I'm going to, as an example lecture, what kind of theoretical detail we are going to be uh, conducting this semester, I'm going to talk about this phylogenetic tree problem, which I will, some of it may be repetition when the time comes again in the schedule. But so let's download this one. So that the main reason is to whether you have the sufficient background. The main reason I'm going over these slides is to see, to give you an example to whether you have the sufficient background to follow the course, okay? And then you may decide on your own. It's not this one. Phylogenetic trees, yes, right here. So it's a week 7 course actually. But the algorithm, I'm not picking the most difficult algorithm in this course as an example. I really wanted to be an average example. So this is the material that we will be discussing in week 7. But let me remind you the problem that we're dealing with. Phylogenetic trees. Our goal is, oops, I went to the last slide immediately. The goal is to build a hierarchical structure that shows the relationships among a number of objects. These objects may be whole organisms themselves. For example, we may have the animal kingdom. So people try to, in phylogeny is a very old term that was coined in I think in the late 19th century to organize the life on Earth as the tree of life in a tree of life. But these days, we usually use phylogenetic trees. With the help of the genetic information, we can relate organisms better to each other by using their genetic information, not by just looking at their appearance. Like, for example, a bat may be classified under the birds, but we know that bats are mammals, so they should be actually classified under mammalians. Okay, so phylogenetic tree is basically to build this tree of life, to organize the hierarchy, to show the hierarchical relationships. Close by objects, in terms of their genetic properties, they should be close on this tree. They should be clustered together. And far away objects, they should be far away from each other. So there are different. So it was actually in the second half of 19th century. This is the term coined by Haeckel, and is defined as the line of descent or evolutionary development of any plant or animal species. So let me just show you different trees. For example, this is a phylogenetic tree, which is for different HIV virus strains, I think. These are the virus strains. And look at this tree. This is a tree which is unrooted. If you're from computer engineering, when we have a tree, it's usually like this, right? Let me open up GIMP and a new whiteboard. So a tree structure is actually a tree is a specific graph, which in which we have nodes. These are nodes or vertices. Okay, we have nodes, and some of them are leaf nodes. These are, so this is a tree with 1, 2, 3, 4, 5, 6 leaf nodes and a total of 10 nodes, right? 1, 2, 3, 4, 5, 6, and actually 5 of them, 11 nodes. So this is a tree with 11 nodes. Any tree with 11 nodes is going to have exactly 10 edges. You can find it without counting. We have 10 edges. So a tree with n nodes have n minus 1 edges. And there is a unique simple path between any two of these nodes. These are the leaf nodes, and these are called the intermediate nodes. There are 5 intermediate nodes and 6 leaf nodes. So this is a binary tree because each intermediate node has 0 to or 1 to 2 children. If it has 0 children, it has basically, it's a leaf node. Okay, nodes with no descendants, no children, are called leaf nodes. And this is when we draw the tree like this. we designate this one as the root node. So this is like a rooted tree. But if you look at just the nodes and the edges as a graph is nothing but a set of vertices and a set of edges. Okay, so in our set of vertices, these vertices will be just these nodes n1, n2, all the way to n11. If I name them like this randomly, n1, n2, maybe this is n3, just randomly, I'm labeling them randomly. Okay, so this is a set. The set of vertices is this 11 nodes, and the set of edges is nothing but tuples that shows undirected edges between. For example, there's an edge between n2 and n3. Okay, this may be undirected like this. This is also a tree. You may also make them directed to show the ancestor descendant relationship. For example, n2 is a child of n3. In order to make it like so, you may have directed edges like this. In that case, if you have directed edges, you're basically also you're defining a root. The node with no incoming edges will be the root node. Okay, so the outgoing edges are called, sometimes the number of outgoing edges is called the out degree. The number of incoming edges is called the in degree. So this is basically a tree, but usually we don't have these directions. These will be just tuples of nodes, and there will be exactly 10 tuples here. So this is going to be our tree. And in a binary tree, there will be at most 2 outgoing edges in a given node. Okay, so this is a binary tree. So our goal, but as I said, we could have taken this one, if consider them as undirected edges, we could have taken this one and pull it out like this. And this may be made a root. Okay, this may be the root node, and these two may be the children. So basically, we can have unrooted trees like this, and any node here may be the root. This can, and it's not, in that case, it's not going to be a binary tree if you make this one root node, because there will be 3 intermediate nodes that are going out of it. Okay, but any leaf node here could be made a root node easily. Okay, and these branches will be the intermediate nodes. So there may be trees that are rooted, unrooted, but my main goal here in this class is to talk about an algorithm. And here is the problem that we're going to talk about. I'm going to go over and repeat the slides in these previous in these previous slides later on week 7. But here is the computational problem that we are going to discuss, the distance-based methods. And I'm going to talk about maybe the neighbor joining algorithm and UPGMA. And both of them are greedy algorithms. Oh yeah, I can actually magnify the pointer size. Let me do that. Display settings, no, not the display settings. I think it's about in the mouse, right? Settings, mouse, settings, mouse. Yeah, I will do that. Sorry, I didn't. Yeah, it's just 1 minute ago. Mouse settings, change mouse settings. The magnifier, yeah, here. Change pointer size. So yeah, I think it's going to be, this one is going to be better. Okay, so I'm going to we're going to talk about distance-based methods and neighbor joining and UPGMA, and I'm going to first describe the problem and then talk about the algorithm to solve this problem. All right, so you're welcome. So let's start with the problem definition. So as input, we are given a matrix. It's called a distance-based method because this matrix shows, as I mentioned earlier here, this matrix gives us the pairwise distances between objects. Imagine we have these objects, maybe cities. Okay, we have n cities, and here, in terms of the distance between them, the number of kilometers to go from one city to another. In that sense, this matrix is going to be a symmetric matrix, because O32 and O23 are the same thing. I mean, going from Ankara to Eskişehir and going from Eskişehir to Ankara takes the same amount of kilometers. So we are going to be given a certain distance matrix, and this distance matrix may have some properties. One property is this being symmetric, and if they are really like Euclidean distances on the 2D plane between these two objects, this property that we have on such distance matrices are called additive distance matrices. Okay, additive. Additive means that it's like not only the symmetry, all the distances are greater than 0 if there are two different objects, and the distances, the diagonal is all 0 because the distance of an object to itself is 0. All the other distances here on this matrix is non-zero and strictly greater than 0. It's a symmetric matrix, and for every triplet of 3 objects, I, OI, OJ, OK, okay, if I take triplets of objects here, the triangular inequality holds. What does triangular inequality mean? If in a triangle that is on a plane on the Euclidean space, what happens is that we cannot have arbitrary distances between these 3 vertices of these triangles. If I have 1, 2, 3 vertices, if the distance between 1 and 2 is d1, 2, the distance between 2 and 3 is d2, 3, and this is d1, 3. This one always holds. So if I add d1, 3 and d2, 3, it's always greater than d1, 2. Okay, so this inequality should hold for all the edges of this triangle. Okay, so additive matrices are like this. The good thing is that for additive matrices, this problem that I described earlier, is it possible to build a tree such that the 3 paths are equal to the distances on this given input matrix? So this is my input. By the way, let me just describe the problem. So we are going to be given this input matrix, and our goal will be to generate a binary tree in such a way that all the objects are at the leaf nodes. Okay, for example, if I have 11 objects there, this tree should have 11 leaf nodes. Okay, I'm going to arrange them in different order at the leaf nodes, and I'm going to associate weights. For example, 1, 2, 3, 1, 2, again another 3, maybe 5, 6, 1, 4. So if I have these, I'm going to also assign these edge weights in such a way that if I take any object here, if this is node number 3 and this is node number 5, in the matrix, the distance between n3 and n5, which is, if it's somewhere here, this distance, whatever given in the input to me, should be equal to the path distance between n3 and n5. And since it's a tree, there is a unique path between n3 and n5. It's this distance, 2 plus 2 plus 3 plus 3 plus 4. So 4, 7, 10, 14. So it's 14. So in the matrix, in the input matrix, it should be written as 14. For additive matrices, there are efficient algorithms that exist to make this matrix, to make this tree exactly with exact equal path lengths to the given input matrix. Now, here is the thing that makes the problem different. If you're not given an additive matrix, if you're given a matrix in which the triangular equality does not hold, okay, there may be, it's not even a matrix. I mean, it may not even be symmetric, but most of you will be given symmetric matrices, but certain distances, for example, the edit distance between two sequences, or the sequence similarity values between two sequences, these things are not additive. In such a case, if the matrix is not additive, it will be impossible. Okay, now what I'm saying is that it can be proven that if this given input matrix is not additive, it's impossible to construct such a tree. So such a tree doesn't exist, because the three path lengths on a binary tree like this, they are by definition, the three paths, not by definition, but you can prove that they follow the triangular inequality property. They're additive. So if the input matrix was not additive, it means that it's not possible to show them as a tree like this. Now, in that case, I'm changing the problem to something else. Let's have the three path distances. I can have these three path distances represented as a matrix itself, right? Let's call this matrix the small d matrix. The d matrix here is the matrix that show the three path distances on the tree. And this is my input matrix, capital D. Now, if it's impossible to have D, my goal was to have D is equal to D, okay? If it's additive, the input matrix is additive, this is possible. But if the input matrix is not additive, this is not possible. Then why not change this problem into an optimization problem? In the sense that find a tree that minimize the difference between these two matrices. Okay, so the difference between these two matrices is defined as the summation of absolute values of the differences between all individual cells. Okay, so the difference from this one to this one, the difference from this one to this one. So between these two matrices, if you add up all the differences in absolute values between individual corresponding cells and sum them up, okay, if you sum them up, so in other words, for example, dij, yeah, actually, for all ij, get the difference between dij and small dij and large dij, take the absolute value and sum all of them up. And whatever this distance is, find the tree that minimizes this distance. That becomes an optimization problem. And the decision version of this problem is the NP-complete problem. The decision version is something like this. Is there a tree in which this distance is 5 units or less? Okay, so that's the answer to this question is just yes, no. Okay, and in order to be able to answer this question correctly, you actually need to solve the optimization problem, okay, to find the minimum one. So, yeah, as I said, this problem, the optimization problem is the difficult problem when the matrices are not additive. Now, I will actually talk about now in the remaining 20 minutes, not the UPGMA or neighbor joining, but I will describe you an algorithm which is going to give us the correct matrix if the input, correct tree, if the input matrix is additive. This algorithm does not have a name. It's an iterative algorithm. And it's not greedy. Since we know the matrix is additive, it's always going to find the exact solution. Okay? The given input matrix is going to be, the input is going to be an additive matrix. The first step will be to verify that the input matrix is additive. After we verify that it's additive, the algorithm is going to be like this. Okay, so let's actually, I may try it on an example additive matrix. So do we have an additive matrix here? Yeah, this one. Yeah, so let me just copy this one. I'll just take the screenshot. I think it was, no, yeah, I remembered it correctly. So let's take this matrix, copy it in our, I'll copy it here. Okay, so this is my input matrix. The first step is to verify that it's additive, and let's assume we did that. So we need to look at all the triplets and check whether they satisfy the triangular inequality. Now, here the algorithm proceeds like this. So let me just image, flatten image. Yeah. Now, the algorithm proceeds like this. We start with a random edge, okay? And that's going to be the first edge in our tree. This is going to produce an unrooted tree first, but we may take any one of the nodes and make it the root node. So let's start with an arbitrary edge. By the way, they are all actually, there is no reason the ones that are at this first row are lowercase letter. They are all actually capital. So I have these objects A, B, C, D, E. 5 objects that I want to construct a tree among them that obeys these distances between them. So let's start with an arbitrary edge, for example, between B and E, we may start, or for example, maybe A and D. Just pick an arbitrary edge. Okay, so this is going to be the first edge in my tree, A and D. The tree starts like this, A and D, and the distance between them is 8 units long. Now, what I'm going to do is I'm going to pick, again, randomly, another node, B, C, or D, which is not currently in my tree. And I'm going to connect it to this tree in some random branch between two nodes, between two random nodes. But currently my tree contains only 2 nodes, so it's going to be between A and D. And I'm going to form the linear equations to find out where this node actually is. For example, should we choose E here? Yeah, or BC, from BC and E, anyone you want to choose to put between A and D? Any ideas? I mean, any choices? Because since we are doing randomly, BD, yeah, let's choose B. We are not choosing an edge actually at this point. We are choosing a node. In the second step, we will be choosing a random node from the remaining nodes. So let's choose B. Okay, now what I'm going to do is, and since AD is the only 2 node here, the algorithm proceeds like this. I'm going to put B here between them, between A and D. But what I don't know currently right now is this X, Y, Z, these values, where this branching, where should I put this intermediate node, and what this X, Y, Z is going to be is unknown. I can put it anywhere. Now, I'm going to put this B in such a way that it's actually obeys the distances here. So what do I know about X, Y, Z? I know what X plus Y is, right? I know what Y plus Z is. And I also know what X plus Z is. What are these? They're in the input matrix. X plus Y is equal to distance between A and B, which is 10. Y plus Z is equal to the distance between B and D, which is 4, given in this matrix. And X plus Z was the distance between A and D, which I already know, which is 8. Okay? Now, by using these 3 equations, can I find out what X, Y, Z is? And the answer is yes, because these are linear equations. I have a system of linear equations, 3 unknowns, 3 equations. I should be able to uniquely find what X, Y, Z is equal to. For example, from here, if I multiply this with both sides by -1, X minus Y is going to be equal to 4 as well. Okay, so I multiplied this one with -1, and I added these 2 together, which got rid of the Z, since it's multiplied with -1, and this became X minus Y. 8 minus 4 is equal to 4. Now I have two equations, x plus y is equal to 10, x plus minus, so this is 10, oops, sorry, x plus y is equal to 10. Again, if I add these two equations, 2x is equal to 14, which gives me x is equal to 7. So if x is equal to 7, I'm going to write 7 here, 3 here, x plus y was 10, and b plus d was 4, right? And this is going to be 1. So right now, the tree is going to look something like this. Let me copy this part. Sorry. Let me copy this one again to a new slide. And again, flatten my image. And all right. Now the tree we have found with A, D, and B is something like this. This is A, this is D, this is B. I mean, the length of the branches do not respect the things that we have found actually, but it was like this. Okay, so right now this is the current state of our tree, and we are going to continue doing this for the remainder of the nodes. For example, I'm going to the remainder of the nodes are C and E. For C, I'm going to pick a pair of nodes on this tree and try to put C and C in between them in a certain location. Let me change my pen color. Now let's try to put C here between AB. I can put C either between AB or AD or BD. So there are 3 pairs, right? I have 3 pairs of nodes between them. And among these 3 pairs of nodes, I can decide to put C in between any 2 of them. Now, the only thing in this algorithm is that if after you solve these linear system of equations, if the branching occurs from an existing branch like this, for example, if I put C here between A and B, and it turns out that this X right now also turns out to be 7, if C also branches from this exact same intermediate node, it's bad for this algorithm. I need to pick a different pair. So putting AB between putting C between AB is a bad thing because it's going to mess up the other pairwise relationship between the nodes. So that's the only thing in this algorithm. So to sum up, the algorithm is like this. Let me show you this. This is the entire algorithm in pseudocode is described on this slide. The first step is verifying the distance matrix is additive. We choose a pair of objects, which results in the first path in the tree. This is what we did with AD. We choose a third object and establish the linear equations to let the object branch off the path. This is what we did with B. And we repeat this last step until no remaining nodes left. We choose a pair of leaves in the constructed tree constructed so far and compute the point at which a newly chosen object is inserted. If the new path branches off an existing node in the tree, we do the insertion step once more in the branching path by using a different pair of objects. If the new path branches off an edge in the tree, the insertion is finished, and we repeat this step for another newly chosen object. So this is a very simple algorithm actually, and we repeat this until the entire tree is constructed. You may continue doing this as an exercise, for example. Let's try to, we can actually finish this easily. Let's do C now between A and B. So I put C here, okay, but I don't know, this branch may be towards E here as well, for example, because depending on what X, Y, and Z is going to turn out, this can either be to the left of this branch or to the right of this branch. But let's just have these equations again. I'm going to label them like this. X plus Z is going to be equal to the distance between A and C, which is 12. x plus y is equal to 10, the distance between A and B, and y plus z is the distance between B and C, which is 4. Okay, I can again get rid of z here, the same way I did earlier. X minus y is going to be again equal to 8. So I multiplied this one by minus 1. And this z's are cancelled. X minus 1 become 8. X plus y is equal to 4. X minus y is equal to 8. No, for the in this case, we don't compute the BD distance. We don't use the BD distance because we choose to put C in between A, B. So this BD distance is not taken into account because we have a three equations, system of linear equations of 3 unknowns, and we try to put C in between them. But if this branching is not from an existing node, it will also be correctly putting C and respect the distance between C and D in the matrix. And we'll see that, for example. If the branching is not via an existing node, we'll see that the distance between C and D, or the distance between all of them, will be correct in the tree. So here 2x is equal to 20 and x is equal to 10. So I just edit this one and this one to find 2. Oh, I did it wrong, right? I already used this one. So it's actually 2x is equal to 18, not 20. So if x minus 1, 8, x plus y, 10, 2x is equal to 18. Now x is equal to 9. If x is equal to 9, what does this tell me? This tells me that this is actually, C actually branches off right here. The branching is right here because since x is 9, this was 7, distance of 2 is here. So this is 2, is the total distance. X will be 9. X is from A to the branching. And this is what C is, not this. Okay? Now, this x is going to be equal to 9. Z is going to be equal to 3. What was Z? Z was from the branching to C. So this is going to be equal to 3. And the other part we named was Y, right? Which is going to be 1. And this is exactly going to be, so this is going to be 1. So the distance from this branching to this one is going to be 1. So 3 plus 1 is 4. So the distance between, so let me just draw the tree from scratch here. It's a little bit crowded over there. So I have C, A, B, C. So this is A, B, sorry, this was D. This is B, this is C. So if we draw it again, it's going to be like this. So this is 3, this is 1. The distance, we have this thing here. This point here was 1. Okay, we already had this as 7. Now this is 2 here, and that's it. So these are all the branches: 7, 1, 2, 3, 1. Okay, if you look at this, the distance between C and D is this time 6, and that's correct. Okay, distance between C and D, 3 plus 2 plus 1. On my tree, it's 6, and it's correctly 6. Okay, so this is my tree like this. And finally, we are going to add E here. I can try to add E between A and D, and it's going to continue like this. So this is an iterative algorithm with potential repeats in between. When we failed, we didn't see the case where the branching off was from an existing node. But if it happens that, for example, if in this case here, if x turned out to be 7 instead, if x was 7, the branching would be of an existing branch. And we would just ignore everything we did here, and we would repeat it, to repeat the insert C between a different pair of nodes. All right? If x had turned out to be 7, which didn't in this case, but if x had been 7, then this would be bad for us because the branching off would be from an existing node, and we would have to repeat the addition of c between a different pair of nodes. Okay, so the pseudocode of the algorithm is fairly simple. Now, if we talk about the computational complexity of this algorithm, it seems like the number of steps we take here is, the first 3 steps are actually this step, verification of the matrix, whether it's additive or not. It's O(n) cube, but still polynomial, because for every triplet, we have to check whether it satisfies the triangular inequality or not. So it's going to be O(n) cube to verify the matrix that it's additive. So the first step is O(n) cube, and then the second step, we just choose a random pair. It's O1. It's constant time. We do it in a constant number of steps. And the third object, choosing the third object and solving the system of linear equations of 3 unknowns, again, is constant time. It's also O1. So these 2 steps, both of them are O1. Right now, this is O(n) cube, which is dominating the complexity. And what about this step? Choose a pair of leaves, and what's the worst case complexity of repeating this? Just if we were successful in the first step, so there are n-2 remaining, not n-2 actually, n-3, because we have already put 3 of the nodes in the tree. So this loop is going to run for n-3 remaining nodes. And if we are successful the first time for each of them, it just takes O(n). So it's because adding each one of them with the system of linear equations is solving this is going to take constant amount of time. So the entire loop is going to be O(n) in the best case, linear. But what if we were to repeat this again and again? How many times are we going to repeat it? For example, if half of the nodes are already in the tree, there are O(n)² pairs of nodes in the tree that are currently in the tree. So we may need to, if we are unsuccessful in the worst case, if you're unsuccessful in all of them, we would have to repeat addition of a single node O(n)² times. So in the worst case, this entire loop is also going to take O(n) cube time, because if I write it here, it's not this one, GIMP, file new. So if we try to write it here, in the worst case, there are this many pairs of nodes in my tree at an intermediate step. Actually, if it's in the ith step, there are I choose 2 different pairs of nodes in the tree because they're. And what we will do is I choose 2 is equal to I times I minus 1 divided by 2, which is OI². Okay, so which means that you may have to try this many times in the worst case for a single, in the ith step for a single node. And since there are in total n steps in my, O(n) steps in my loop, and if each of them take OI² time, the total final complexity will be O(n) cube. So this algorithm that we have seen here is a polynomial time algorithm. In that case, it's considered efficient, but it may be prohibitive if you have 1,000,000 nodes, for example. O(n) cube will not be prohibitive. If you have 1,000 objects that you want to cluster or build a phylogenetic tree for, O(n) cube is still going to run in a couple of seconds or so. But it will be prohibitively expensive. It may take hours or maybe days if you have a lot of objects to cluster. Okay, so this was an example algorithm and example discussion of computational complexity. And in terms of space complexity, it's O(n) square. The memory that we are going to need, the input is O(n) square anyway. We have that many. Our matrix size is O(n) square. So where is the flatten images here? So and the tree itself is also the tree is linear actually. The tree is going to occupy only. Oops, didn't flatten the image. Anyway, let me write here. So the input is O(n) square, but the tree that we're building is linear in size because I have n nodes and n-1 edges. So in terms of space complexity, it's O(n), but the input itself is O(n) square. So that's what space complexity is, and we also discuss computational complexity. Exactly. I'm talking about, when I take O(n) step in the best case, the first step, since the first step is O(n) cube already, even in the best case of this loop, I was talking about the best case in the case of this loop. It's going to take O(n) time because for all of them, for all the elements, not just one element. Just one element because one element takes constant time. Okay, we just add it in just by solving a constant number of system of linear equations with three unknowns. That three is constant. Okay, it's always going to be three equations, three unknowns. Whether it's the ith iteration or nth iteration, it will always be three equations, three unknowns. So it's constant amount of time for a single insertion, for a single successful insertion. If you're able to do the successful insertion in the first step, it means that we are able to do the insertion in constant amount of time for a single node. So for a single node, it's O(1) time. And since we run the loop for the remaining n-3 nodes, which is O(n), that makes the best case is O(n). Okay, but this best case being O(n) actually is dominated by the first step, which is O(n) cube. So the algorithm's complexity is O(n) cube plus O(n) for the best case, which is O(n) cube. All right, and in the worst case, it's going to be O(n) cube too. So so regardless of whether we are successful or not in this loop, we have the worst case or not in this loop, verification of the matrix, whether it's additive or not, it's going to be the most time-consuming step actually. All right, so this was an example discussion. As you can see, we talk about abstract things, trees, an arbitrary input of different size. We will be discussing algorithms like this in class, and if you were able to follow it nicely, you're welcome to add the course. Okay, so I'm going to now again share the link for the enrollment list. So this is the Google Forms, and you're free to write your name, surname, student ID in this form. And all the students that submit their student IDs and names, they will be able to add the course during the add drops. Okay, there will be no capacity limit or so. All right, that's it from me for today. I will stop the recording.